Hello, everyone. Good day, good morning, good evening, to depending on which geolocation you're in. My usual first question is, can you hear us? Can someone please say in the chat? Can you hear us? Can you see two gentlemen on screen? Okay, thank you, Elias. Thank you very much. So it's been a while since our last Stark at Home. We took sort of a break, but it's now time to get back to stuff. And we're going to try and do this regularly, roughly once a month. A lot of very exciting topics that I'll mention, some stuff about tokenomics, looking at Fry versus KZG and various proving techniques, new updates on the prover technology. I'd like to do one on the vision of Starknet and a whole bunch of other topics. And what's unique about Stark at Home is that we try to take some very deep topics that usually, you'll best learn or understand by reading a lot of papers, or in today's session, it's more about code. And we try to break it down to something that's a bit more conversational. And today with me, I have Gidi Kempfer, head of core engineering at StarkWare. And we'd like to tell you the story of Stone, which stands for Stark 1. It is the very first prover that we've been using in production probably more than 4 years, I'm guessing. I like to think of it as something like a 747. It's this very reliable and trusted working horse that's not just has been around for a while and hauled a lot of traffic, but is also in use today. And I think to me the 747 is this concept, right? The Boeing 747 of something that's been around for a while, is extremely reliable, does a lot of work. And I'll hand it over to Gidi to tell us the story, first of all, the history of Stone. And then once in a while, I'll ask some questions, and also we'll pause for questions by the audience. I see that the Crowdcast interface has changed. You probably see a Q&A button, and then you can press it and type something like test question, and then you'll see that people see it. So please, for the questions, please use the question button and not the chat, because the chat just gets diluted. So without further ado, Gidi, first of all, can you please introduce yourself and then tell us the story of Stone's history?
Sure, thank you, Eli. Well, I have a background from about 25 years of working in the high-tech industry, various startups, mainly in the telecom domain, typically in technical leading roles. That's also how I joined StarkWare. So I joined when the company was founded, just after the founders, and been with the company since. Today I'm managing an engineering group, and in particular responsible for the group developing improving technologies at StarkWare. So I'm getting feedback, Ellie. Maybe you can mute yourself.
Yeah, so let's go back to the very start of how Stone came about. So ZK Starks is a technology that can be used for privacy or scalability. And if you go and scale something, so the first question is, what do you want to scale and how do you go about scaling it? So can you take us back to the very early days and what were StarkWare's thought processes, and how do we end up having something like Stone?
Yeah, so well, when the company began, we didn't have a clear idea of where we wanted to take proving technology. And if you could mute and get in there.
Yeah, I will. Sorry. Yes. I just need to find the button for muting myself.
Somewhere on the right-hand side. Yeah, thank you. So in the beginning, basically it began from the Stark proving algorithm developed by yourself and and other people in the academy. And it was clear that there was the ability to perform zero-knowledge proofs. There was the ability to perform proving of computational integrity. And the question was, where did we want to take this technology? There were various directions. I think the foremost two directions that we were considering were privacy, given that zero-knowledge proofs allows hiding information. And the other direction was scalability. And actually, we pondered this for quite some time, and eventually decided to go for scalability, actually, which was, I think, quite revolutionary at the time. It wasn't the de facto choice. And why scalability? Because basically the Stark algorithm allows proving the computational integrity of programs running at, let's say, n steps in a way that verifying the proof of the correct execution of a certain program would take a logarithmic number of steps. So if you do a logarithm of the runtime, that implies very efficient scalability of verification. Which implies in various constellations that people who don't want to do the computation, or a blockchain that doesn't want to do the native computation, can save a lot of energy, cost, time, whatever you want to measure. So that's where scalability came in. So it was obvious we could start proving for scalability. The next big question was, what is the use case most desirable, or which use case needed scaling first? And we took a look at the various applications that were out there on the blockchain, and it was quite clear to us that the biggest or the highest level of traffic appeared in exchanges, in crypto exchanges in particular, mainly on centralized exchanges at the time. And we decided to target this specific niche and accelerate that first. So we sat down and thought about developing a system that would accelerate proving of the correctness of transactions on the crypto exchange. And in fact, this was the first application that we developed using Stone. At the time, we partnered with a company running a decentralized exchange. Today it's known as RhinoFi. At the time it was known as Bitfinex, later on Diversify, and now RhinoFi, as I mentioned. That's the first StarkEx exchange that we built. We used Stone to prove the correct execution of basic crypto transactions. At the time, well, basically, if you think about the Stark algorithm, it talks about proving, and now I'm going to swear a little bit in algebra, it talks about proving the low degreeness of polynomials on finite fields. So, end of swearing. This has nothing to do with exchanges, has nothing to do with programs, at least not directly. So in order to do a reduction from proving the correct logic of a crypto exchange using terms from low degreeness of polynomials, basically we needed to build handcraft polynomials that would express things that we could actually show corresponded to things that happened on the exchange. So we call this an AIR, or an algebraic intermediate representation, which basically is a set of polynomials and constraints over those polynomials that express the business logic that we want to prove. So the first version of StarkEx at the time, that is the system that used Stone, was using Stone to prove an AIR, as I mentioned, for a specific use case called the StarkEx, or crypto exchange. Clearly, this was quite laborious process of developing these specific polynomials that we needed to use. And when a few more customers came along, we understood that every time we wanted to add new features, for instance, not just a cryptocurrency exchange, but we also wanted to implement functionality for, let's say, an NFT exchange, doing this every time by handcrafting polynomials was very, very slow, cumbersome, and not flexible enough for what we needed. Along came dydx at the time, and they even wanted to have us implement business logic for derivative exchange, which was another level of complexity. So in parallel, the idea came up, credit to Shachar Papini and Lior Goldberg from StarkWare, to actually build a virtual machine on top of Stone, basically a virtual machine expressed as an air, as these polynomials, on which we could actually run programs written in a specific language, which we call today Cairo. And this language enabled us at the time both to increase our velocity of development of these. Instead of developing airs or polynomials, we could just write programs that we wanted to prove. And it also turned out that it wasn't just a matter of velocity, but we could actually improve the efficiency of our proofs because we could implement much more sophisticated algorithms in terms of what we wanted to prove, which were much more difficult to express in straightforward polynomials. So this is how Cairo came to life. So we initially used it in-house in order to increase our development velocity and to be able to develop very complex expressions to be proven by Stone, and continue to output systems, multiple layer 2s built on StarkEx for the various use cases I mentioned. And at a certain point, we understood that we still had a lot of engineering overhead to develop these systems. Because every time a customer would come along and say, I want to have this and this feature in StarkEx, we still needed to sit down and program the specific Cairo logic in order to implement that in these systems. That took time, that took effort, and we were becoming a bottleneck in that sense. And at the same time, customers were also, because of this bottleneck, asking us to be able to develop these features on their own. They actually wanted to be able to have unique features that other customers of ours didn't have and things like that. So here, the idea of a multi-purpose, general-purpose platform came up, and that very quickly evolved into the vision that we have today of a permissionless general-purpose network, which we call Starknet. And the prover underlying Starknet remained the same prover. It remained the same technology, the Stone technology, Stone prover. But we were now talking about multiple StarkEx systems, Starknet as a system. And initially, each of these systems were running their own Stone prover. And those proofs were being submitted on chain. And the idea came up to share the prover among these multiple systems and create large proofs that could include statements or things to prove from these various systems together. And the idea here is that because of the logarithmic scalability or the exponential scalability, if you like, of the Stark algorithm, combining a much larger statement and proving that at once, so a statement that says basically, here's a statement from system A, and here's a statement from system B, and here's a statement of system C. We could prove that as one big program. And submitting one proof to Ethereum is roughly the same cost as submitting one proof for many, many statements because of this logarithmic scalability, which resulted in what we call Sharp today, which is a shared prover where multiple systems or multiple sources can submit different programs for proving. Underlying Sharp is the same Stone prover, which generates proofs that are later submitted on chain. So this is roughly where we stand today. And given that Starknet has become a community effort, an open permissionless effort, a lot of the code in Starknet today is already open source, and it became only natural to open source Stone as well, which is the current state. I'm muting bottom right somewhere. I unmuted you, I think.
Yeah, I can't find. They changed. Can you hear me now?
Yep.
Apologies to our audience. They changed the whole interface of this website. It looks much nicer, but in particular, it's harder for me to find the anyways, to find the controls. So I apologize for not unmuting. Maybe let's pause here to answer some questions before we move on to the next topic. So I see one question is, when will StoneProver be compatible with Cairo 1 programs?
Excellent question. In order to, I think I need to explain the question. I'm going to mute you anyway. Okay. I'll explain a little bit about this question. What do we have in the open source right now? In the open source, we have a StoneProver, and it comes together with AIR, this arithmetic intermediate representation. It's the AIR for the Cairo virtual machine. The Cairo virtual machine runs an assembly language called CASM, or Cairo assembly, if you like. And CASM is the result of compilation of a language called Cairo as well, but in a higher level form. This Cairo could be the first version of Cairo, which we also call Cairo 0, or it could be the current version of Cairo, which we call Cairo 1. With the tools provided with Stone, it's very easy to prove a statement written in Cairo 0. Why is that so? Because these tools are compatible with Cairo 0, but unfortunately, they're not compatible with Cairo 1. And therefore, this question is, when will Stone support Cairo 1? In order to support Cairo 1, basically, we need to add functionality to the tool chain that allows proving Cairo 1 statements. The reason that this was not open source is that, in fact, we don't really have this tool chain in-house, as much as it may sound surprising. Despite the fact that you can write Cairo contracts on Starknet and Cairo 1, the actual statement that Starknet proves using Stone is a Cairo 0 statement, which is an implementation of what we call the Starknet OS. The Starknet OS program is written in Cairo 0, and it receives as input transactions that are compilation of Cairo 1 statements, or if you like, transactions. So the tool that we use in order to use Stone to prove Starknet statements is basically this Starknet OS. Clearly, that's not very useful for the general community. And there is work in place in order to create a toolchain that would directly allow proving statements written in Cairo 1. That's being developed in the community, in fact. It's also planned to use that with various open source projects out there. And it's clearly in demand in the community. But I don't have an exact timeline for when that will be ready. As I mentioned, it's being developed in the community and not by ourselves. Let me see if I can. Yeah, Eli.
I hope that by the end of the show, I'll be able to find out where they hid the unmute button. So next question is, what about Cairo 2? I think I can answer that. Right now, there is no Cairo 2. In fact, Cairo 1 is Cairo, and we hope it's going to be with us for a very long time. That's the plan. So there's just Cairo. But, you know, just like Rust or Python or other languages get like, you know, not exactly refreshed, but augmented all the time with backwards compatibility. You can expect the same to happen with Cairo. So you'll see versions and whatnot, but there's just Cairo. And then the same answer Gidi just gave applies. So next question, what benefits using StoneProver? Will it reduce gas cost and increase TPS? Is there any other advantages of using it? Gidi, do you want to take that? I'll try to mute. Let me just.
Try to unmute you anyway. As I mentioned in the beginning, you could use the stone prover for anything, any use case you'd like. It doesn't necessarily have to do with a blockchain use. So you can just write a program in Cairo. All right, it's limited today to Cairo 0, but imagine Cairo 1 if you like, and prove that program. Maybe use that proof somewhere off-chain, maybe use it on some verifier contract that's deployed on a network, on Starknet, on Ethereum, or just give the proof to someone else that needs to get that proof. It could be a zero-knowledge proof if you add zero-knowledge functionality to Stone. In fact, strictly speaking, Stone today is not zero-knowledge, but it could be added to the code. And you could use it for a scalability application. You could use it for a privacy application. So basically anything that you would imagine using a prover for. If you want to use it for the scalability application, yes, you could use it in order to effectively increase the TPS of the underlying network. So let's say Ethereum, what we do in our systems is basically we run some business logic off-chain. That's how Starknet works. And then the correctness of this business logic is proven using Stone to Ethereum. And Ethereum accepts that proof or rejects that proof, depending if the proof is correct or not, of course, using a verifier contract that's also open source and out there and deployed on mainnet, as well as other Ethereum testnets. And you could use that to build your own layer 2, or you could use Stone to submit proofs to a Starknet contract implementing a Cairo verifier and use that to implement layer 3. And given the logarithmic compression that Stone does, the effective transactions per second running off-chain is multiplied by this logarithmic factor versus what happens, or is divided by this logarithmic factor, if you like. Compressed to allow verification in much less than what the original transactions would have cost and would have taken on Ethereum. So that's the scalability approach. This saves gas. And of course, increases the capacity of the network.
Yeah, no, I just wanted to answer the next question, but sorry, and I need to find out how to just change it on my own and unmute myself. So next question, maybe we'll take one more question and then we'll move on to the next topic, which is, so the next topic is going to be, how do you go about actually designing a prover for general purpose, programs, and what are the considerations if you wanted to run in production on the cloud, interacting with a blockchain. That will be the next topic, and I'll actually run a quick poll. I'll try to use the poll about how many of you guys are actually in the business of building proof systems yourself, or just consuming them. I think it's just an interesting topic, and so I'll run this little poll. So I'll answer one more question, and then we'll move on to the next part of the talk, and then we'll get back to more questions. So Hugo is asking, to my understanding, generating the polynomial constraints is quasi-linear in the length of the computation. If this is correct, how can a verifier check in logarithmic time that the proof concerns the program it wants to verify? Okay, so let me just clarify a few terms here. So a computation is specified in terms of certain polynomials that, like something like x squared should equal y, where x represents a register and y represents, let's say, a memory location. And then, y squared should equal 5. Or each one of these is called a polynomial constraint. Now, when we say that something runs in quasi-linear time, we means that if the number of steps of your computation, let's say, is 1,000,000, then saying that something runs in quasi-linear time in 1,000,000 means it takes you 1,000,000 times a factor that is roughly like the number of digits it takes you to write 1,000,000. That's logarithm. So it's like 1,000,000 times 7, more than 1,000,000. So more than, if your computation ran for 1,000,000 steps, according to this question, something needs to run for more than or the number of constraints is more than 1,000,000. It's 7,000,000. However, we do claim, and I do stand behind this claim, that the verifier coming to verify the program checks everything in logarithmic time, which in our case is like roughly 7 steps. So how can the verifier that runs just for, let's say, 7 steps check something that looks like 7 million, different constraints? So the trick is, the way to think about this is, think about a computer program in your favorite language. The program, think about a program that says for I goes from 1 to 1,000,000, and then 5 lines of code. End of program. So this is something that is specified using, let's say, 7 lines. Let's imagine a little program that runs for 7 lines, but it talks about a computation that will run for 1,000,000 iterations, right? Because you have this loop running for 1,000,000 iterations. Now, this is exactly what's going on. The verifier, the Stark verifier, only needs to know the analog of this short computer program, where in our world it would be converted into a set of polynomials, but the number of polynomials, taking this example, would be 7, let's say 1 per row. Now, when the prover does the computation, sure, the prover will need to run something for 1,000,000 steps. And each time this thing is done, it will need to make sure that it fills in a certain table, a computation trace, so that the same 7 constraints applied again and again and again are always satisfied. But finally, when the verifier comes and checks, it's a little bit like it comes and just checks one random location. I mean, it's much more complicated than that, but that gives you a gist of it. So the verifier only needs to run in time that looks like the description of the program, whereas the prover will run in time that is much more than the writing down of the computation. And that's the answer to that. Okay, so with this, I want to move on. I'll run a short poll about just how many of you are, just curious for me, how many of you are, programmers building ZK programs. So now, Gidi, if you can, mute me and tell us about how StarkWare and you went about building a general purpose Stark prover, the stone prover, things like, do you want it Turing completeness? There's one thing that I'll refer to later, which is the field size. Fields, I'll get to that later. But, what kind of interfaces were set with the blockchain, and what are the main engineering challenges that you faced when it comes to things like memory, machine sizes, splitting work between machines, CPU, GPU, FPGA, ASICs, and that whole thing. So Gidi, please take us through it.
Yeah, there's so many parameters to discuss, but I'll mute you again, sorry. There are many parameters to discuss when you want to design a prover. So clearly we were looking at something that had to be general purpose, because we wanted to prove general programs, wanted to have flexibility of writing an arbitrary program. So we went with the Turing completeness of Stark. So for that matter, there was no big dilemma. Of course, in order to implement a language that's Turing complete, that's basically what stood behind the Cairo VM and its design. So you can think of a Cairo VM as a design of a very, very simple CPU architecture with very few registers and very few opcodes that allow you to move from one state to another. So that was not the first decision we made. As I mentioned, we began even before Cairo, but just to mention Turing completeness there. I think in terms of developing the prover itself, we were looking for a prover that could run as fast as possible at the time, whatever we could achieve, of course, using a scalable architecture that would leverage whatever compute power we had at our disposal, typically in the form of cloud virtual machines. So the more cores, the faster, the more memory, the larger the proof we could prove. And those were our initial goals. And at the same time, we wanted to do this in reasonable cost. So one of the features of Stone is its ability to reuse memory it allocated in the beginning, in various stages of the proof for the following stages. So some of the compute fills up the memory, then we throw out of the memory whatever we don't need anymore, and we can fill up the memory again and do this multiple times. We call this concept proving out of memory. If you look at the algorithm of Stark, basically you perform, for instance, a commitment of a very large trace. The size of the trace, of course, is a function of what you want to prove. But de facto, what Stone does, it actually commits to parts of this trace and then aggregates a commitment over the full trace in stages, and each time throws out of memory whatever it doesn't need to commit to anymore. So these kind of tricks reduce the memory footprint significantly, still requiring quite significant memory. The code was initially written to be almost serial, I would say, and gradually parallelized in the various places that could be parallelized. Today, it's almost fully parallelized algorithm that just uses as many cores as you throw at it. So the larger the number of threads or cores that you have on your system, the faster proofs will be generated. We were also experimenting in various technologies out there, GPUs, for example. We experimented with different memory technologies for huge memories even. And we were also always thinking about implementation in hardware, FPGAs or ASICs. I think here the key trade-off is the ability to get available technology off the shelf to be able to deliver in latencies that are acceptable to the applications being developed. And to date, we've still stuck with implementations on CPUs, though we are continuously looking also at GPUs. We feel the performance that we're getting out of CPUs is still sufficient, but it's clear that we can achieve higher performance, sometimes at a higher cost as well, using GPUs. And down the road, maybe also FPGAs and ASICs. As you may know, the velocity of development is higher on CPUs than it would be on GPUs, and certainly on FPGAs or ASICs. So the benefit of being able to change the prover rapidly to add functionality is also something that drives the way it was developed. Then we can talk a little bit about how Stone was embedded inside platforms, inside applications, if you like. So in Starknet, for example, or just you want to build your own application, what do you do with the prover? So the basic concept of using a prover for a system that we took is as follows. You have a certain state that you want to track. Let's say balances of an exchange, or I don't know, ownership of NFTs, or I don't know, in a game, some state of the game. And you think of this as some data structure. State could be represented as a Merkle tree, or could be represented with some other form. And your business logic is basically the rules by which you allow the system to alter the state, change things in the state. Let's say if you want to run a bank and you have multiple balances, then one rule would be that every time you deduct a certain sum from one account, you need to increment one or more other accounts with the exact same sum, so that overall, the liquidity in the bank remains constant. That can be expressed as a rule, and you can add additional rules to that, and you can say a transaction in a bank allows us to transfer money from one account to a second account, and write a rule accordingly. That can be expressed in Cairo. And then what you prove is basically the following statement. The statement you prove is given an initial state A, and a series of transactions applied to that state, let's say transfers of balances, the resulting state is B. So basically the basic statement that is true for all the systems developed to date on stone, I think, is we prove that a transition from A to B is valid based on the following series of transactions. And that is basically the output of the Cairo program that proves this. And that output is then basically sent to stone to be proven, together with additional input maybe that may be hidden or not. And that proof is then submitted on chain to a Solidity implementation of a Stark verifier. The verifier, for every statement it receives, it also registers what we call fact. We call this pattern a fact registry. Basically, it's just some storage element on Ethereum that says that we've seen a valid proof for a certain set of outputs from some Cairo program with a hash X. So this means we've seen a Cairo program, for instance, the Starknet OS, that has a certain series of outputs which say it transitioned from state A to state B based on a series of transactions that may or may not be included here. So that's the hook on Ethereum that can then be leveraged by an application contract, Starknet contract, for instance, that basically holds the state of the entire off-chain system. The state is represented typically as a hash, so you can't really use it on-chain, but it allows us to transition from state A to state B, assuming there is a proof available on the Stark verifier on-chain. And that transition is, we call that the state update function of this Starknet contract or an application contract. Basically what it does, it asks the verifier contract if it's seen a proof for transition from A to B. If the current state on this contract is A, that means that the transition to B is valid and the state gets updated to B. There could also be additional side effects to this proof. For instance, if you want to withdraw or deposit funds to Starknet or from Starknet, that could be handled within the state update in the same smart contract. So that's typically the pattern that we use in order to embed Stone inside the system. This could be used with a simple Stone instance, or it could be used with a Stone shared by multiple systems. I didn't talk about recursive proofs and things like that, but there's a lot of fancy stuff on top of that.
Hi. So one point that I'd like to address that will probably also be a topic of a future episode is that on field size. Stone famously works or is defined over a pretty large prime field, one with 252 bits. And one interesting story is like how or why we chose to do it in that way. So recall, or you'll have to trust me on this, that you can get Starks over any field that is what's called FFT friendly, which means from a mathematical point of view that either its size is divisible by a large power of 2, or that 1 minus its size is divisible by a large power of 2. And there's a large abundance of such fields. And the safety and security of the Stark just doesn't depend on any number theoretic assumptions. So you could have Starks defined over fields that are very, very small, 16-bit fields, 3-bit fields, so on and so forth. And yet, and the smaller the field size, the faster your CPU, GPU, or whatever operations are. And in fact, so before we founded StarkWare, the white paper that describes ZK Starks was in fact actually implemented over a 64-bit binary field. So, however, for production readiness reasons, we decided to go for a large field. And what are these reasons? One, the largest cost is verification cost in Ethereum. That was true at the time when we made the decisions, about 5 years ago, but it's actually still true today. And on Ethereum, the pricing for modular arithmetic is the same up to 256-bit fields. So that metric, which is the main metric that defines the cost of verifying and generating proofs, said that it doesn't matter which field you have. And then for large fields, there are certain cryptographic operations not related to Stark, but related to public key cryptography, things like ECDSA and Peterson hashes and things like that, that are just simpler and safer to define over a large modulus. So because of those reasons, Stone was defined to be over large field. By now, I wouldn't say by now, but looking ahead, you probably want at some point to address latency and have client-side proving at very large scale. And for that, it may be time to revisit and look at also smaller fields. That will be topic for a separate discussion, also to be addressed on Stark at Home. So now maybe let's answer a few questions and then go to the next part of the talk, which is how the Stone Prover fits in the system cycle, the general of what comes before, after, alongside it. So let's. The first question is: could you expand on how an error is represented in each of Chasm's low-level arithmetization, Cairo 0 and Cairo 1? I'll try to answer this question. So the nice thing is that it's one error for all of them. So the ingenious thing about Cairo is that it comes with a very, very succinct and simple set of constraints, about less than 50 constraints of degree 2. And these constraints jointly define something that is like a CPU. So it's a general purpose machine. And then Chasm, Chasm, Cairo 0, Cairo 1, think of all of them as various levels of, here's an analogy. At the end of the day, you have some CPU inside your computer. And then you might be writing in some high-level language, let's say Rust. Maybe it's compiled into some intermediate language, then into some assembly, and then into machine language, right? The CPU stays the same. So in our case, the analog of the CPU is the air. The air stays the same. What you have with machine code or Cairo byte code, which is the lowest level implementation, same. It's one air that addresses it. Above that, you have Chasm, still compiles to the same one air. Cairo 0 compiles to the same thing. Cairo 1, same thing. If there ever will be a Cairo 2, same thing, and so on. So one air to serve them all. Just like a CPU, one CPU to serve all programming languages and also all levels of the compilation stack. Okay, next question. I'll let you answer this, Gidi. Could Sharp publish intermediary proofs so that Starknet block explorers may pack a light client and incrementally validate each new block?
Yeah, great question. The way Sharp works today, it in fact creates what we call a recursive proof. So far we didn't mention the recursion so much, but the way it works is since Stone can prove the correctness of any Cairo program you can envision. In particular, you can write a program in Cairo that verifies a proof. You need to twist your mind around that. So basically, you could prove that you verified a proof. So the basic idea about recursion is that if you take, let's say, 2 proofs and prove you verified both of them and generate a proof of that, you created a proof that indirectly proves the validity of the original 2 proofs, basically compressing 2 proofs into 1. And if you repeat this pattern, you can prove as many proofs as you like, almost, into one single proof that you then submit on chain. and it's very useful for parallelization of proving, using multiple proofs in parallel to compute all these various small proofs and combining these proofs using recursion and eventually proving one proof on chain. And how does this relate to this question? Basically, as you understand from this description, you begin with proving the various original statements. So let's say you have 100 different statements. You prove each and every one of them. These proofs inside Sharp remain inside the system and then are combined together using recursion eventually into one proof that's submitted on chain. What we do today is on chain, we actually create a fact, the same fact I talked about before, for every one of these original proofs. So if there were originally 100 proofs in this recursive proof, we'll create 100 facts on chain. However, it's also possible to envision a scenario where these original proofs are not combined into recursion, or maybe also combined into recursion, and provided to whomever wants these proofs in their own system. This is theoretically possible, or a partial combination of some of these proofs is possible, and that can then be provided to whoever wants that. But you don't get that much of a benefit because you could have created that proof on your own using the stone prover out there. It's the same stone prover that Sharp uses anyway. So unless you want to combine multiple proofs and maybe output a partial recursion, that which maybe could be useful, I'm not sure. Or you could just use the fact that there are facts per proof, facts per original statement on chain, and use each one of these as you like in order to see the validity of every block in Starknet or job in terms of Sharp, as you like. But today, the way Sharp works is that there is a fact per Starknet block on chain. So you could use that, and you could theoretically incrementally validate each of these blocks based on that. The proofs are out there. I hope this answers the question.
Yeah, I'm gonna, we're gonna, let's see the next question. Do both Cairo 0 and Cairo 1 compile to the same CASM CPU air implementation? Yes.
Yes.
Could you talk about last question, and then we'll move on to the next topic, okay. I'll already introduce it, and then we'll answer the question. The next topic is going to be, how does Stone fit into the system life cycle? Sharp, StarkEx, Starknet. And after that, the last part will be what's going on with Stone these days in terms of external projects. This is perhaps the most interesting for those of you who are considering either building proof systems now or doing so soon. So in the little poll that we did, there are 4 people who answered they're building proof systems now, 10 answered soon, 7 answered no. So at least for the 10 who are answering soon, one thing to consider is joining some team that actually is doing things with Stone and making it even more usable and doing new stuff, because there's a lot to do with it. And we'll get to that at the very end. So now to answer this, just one second, let me just test. So could you talk about, I just want to mention, so all questions about things like Stark token and so on, just I'm going to delete them. It's not going to, this isn't the forum for this, and this is about the Stone prover. So, you won't hear answers here about this. Could you talk about Stone inputs? Cairo VM can be run in proof mode to generate a proof. Is it compatible with Stone? Sharp input is PIE. Are some processing done under the hood by Sharp service to feed Stone, or is it directly compatible?
Yeah, and in general, the Pi, there is a format called the Cairo Pi. When generated in proof mode by the Cairo runner, the Pythonic Cairo runner, which is open source, it includes all the information required in order to generate a proof. So basically, those are the inputs required by Stone, etc. There's no business logic associated logic in Sharp that is needed to be run in order to generate a proof using Stone. So everything in the ChiroPi, anything needed by Stone is actually there in the ChiroPi. What Sharp does, it only does some validation so that it doesn't get stuck on things it can't prove. So if you were to submit some kind of ChiroPi that's not valid, or the output of some hacked Cairo runner, then Sharp wouldn't attempt to prove it because it could be improvable. But otherwise, what you find in the ChiroPi in proof mode is enough for Stone to prove. In fact, what Sharp actually does, it doesn't necessarily prove programs directly. It actually proves multiple programs on top of a program called the bootloader. So there is an additional step, and this allows us to pack multiple proofs next to each other. So if I mentioned, like before, I was talking about the recursion, we're actually proving the execution of two verification programs, and these reside one next to the other. So there is kind of a wrapper, which we call the bootloader. You can think of this as a motherboard of a computer or an operating system of a computer that allows running multiple programs without them interfering with each other. They each run in their own memory space, if you like, and it's important for soundness that each of these doesn't interfere with the actual run of the other one. So that's the logic there. For that, you need to generate a specific format, and that's why we call it proof mode of the Cairo runner, but otherwise there's nothing fancy about it.
Okay, so on to the next topic, which is how does Stone fit into the system life cycle? You know, if you talk about systems like Sharp or StarkEx or StarkNet, so they aren't just Stone. Stone is a very important part. It's, you know, the secret sauce or the magic or the engine. If you think of a car, so the engine is the heart of it, but there are many, many other moving parts that come in and before and after it. So, Gidi, can you walk us through where it fits in the grand scheme of things?
Yeah. Actually, I think I mentioned this already somehow. Don't know if you want to go into it again. You can close the slide. Let me see if you can see my screen. Let me know if you can see something, maybe. Okay, so don't know if you can see my mouse, but basically the system is built as some kind of a life cycle. So if we talk about a system using Stone, let's begin on the left top. Basically, you implement your own business logic off-chain. This could be business logic of an exchange. It could be business logic of a general purpose layer 2 like Starknet. And this typically holds state of the system in the form of a Merkle tree or Patriciate tree, or just could be an array of numbers or whatever is suitable for your application. And as I mentioned before, you want to govern the transition from one state to another using a set of rules, which are implemented as a Cairo program, or a series of Cairo programs, if you like, which we typically call transactions. So when you want to change the state of the system, off-chain, you just calculate the effect of multiple transactions over your state, and the result is a new state. And then the program that you send to Stone is basically an execution of all of these transactions, beginning from state A and the resulting state B. And this is sent to a Stone prover. This could be directly to a Stone prover you're running on your own, using the toolchain, as I mentioned before. Or it could be through a third-party service, let's say Sharp, which would combine, would create a proof for you using the inputs or the Cairo Pi, as we mentioned before, sent to the Sharp system. But it doesn't really matter. The two are equivalent in the sense of the life cycle of the system. So in both cases, there is a stone prover somewhere that proves that the state transition is valid. This proof you need to send somewhere to a location where there is a publicly verifiable, immutable registry of the state of your system, which is typically a smart contract on Ethereum, but could be something else. And in order to be able to interact with that location, with that smart contract, you actually don't need to store the proof on chain. You just need to store the fact that you verified the proof. That's what our verifier contract does on chain. So it verifies the proof it receives from Stone via a series of transactions that we send to Ethereum. And then that proof is registered as a fact on chain. Sharp takes care of that for you. So that's the wrapper around Stone, if you like. So there is an application there that just submits the proofs generated by Stone to the blockchain. That's verified by the smart contract of the verifier, and the fact is registered. Then typically, the off-chain application, or Starknet in our case, typically, calls an on-chain contract. This is a Starknet contract on layer 1 to update the states on this reliable registry of the state of the system. And this update state transaction basically calls the contract, which then calls the verifier contract to see if a certain fact was registered. The fact that it's interested in is the transition from A to B, in this case. Excuse me. Sometimes there's a side effect as well. So I want to transition from state A to state B, but part of this transition also results in additional action on layer 1. For instance, the consumption of message, which could result in a new deposit into a system, or writing a new message as output, which could result in withdrawal from the system, things like that. And once that state update has occurred, the off-chain system knows that it's now in a new state and can continue from there. Of course, this is excuse me. This is kind of a simplified cycle. In a real system, the off-chain system would continue to generate new states again and again and again. So the latency until you reach layer 1 could be significant, even multiple hours. But if the state on layer 1 does not advance at a certain point, or maybe this update state transaction gets reverted on chain, that will result in some kind of reorg on the layer 2 on the application, or a halt of your system, depending on what you implemented in your business logic. Because if you're not able to convince layer 1 that the state transition is correct, then everything basically could collapse. Okay, so you don't have the full validation of the correctness of transitions on your system. Depending on your goals, of course, this could be or could not be acceptable. In Starknet, of course, this is not acceptable. So if eventually a proof is not accepted and the state update transaction fails, it will result in a possible reorganization on the layer 2.
Can you hear me?
Yep.
Ah, okay. So I found a different solution too. So let's see. In terms of questions, there's one that isn't relevant, so I'm not going to answer it. Do you think inscription is a good thing or a bad thing on a blockchain? It's not, you know, this isn't the forum or we're talking about the stone prover, not about inscription. So sorry about that. So now I guess the last topic I just want to mention, especially for those of you considering or asking themselves, how can we possibly fit in? I want to mention a number of projects that are already underway that build on top of or improve the stone prover. So first of all, how do you verify the stone proofs? So the way that StarkWare consumes stone proofs is in a very, very particular manner that has to do with a lot of the other components, and this is called Sharp, and there are a lot of other moving parts that would be hard for projects just using or building their own system to use or integrate into. So in order to allow projects to submit stone proofs onto layer 1 Ethereum, there's a project that deals with this, and it's by ZK Security. They're writing a verifier for stone proofs on Ethereum, basically using the existing Solidity verifier and integrating into that. There are some challenges that need to be done, like breaking the proof into a few parts and then composing it and recording things on chain. But this will allow a lot of separate app chains, and just like StarkWare has successfully run systems like StarkEx for dedicated settlement of trades and swaps and whatnot. Now other parties could be doing this once this is live. There's also, Edie wrote this very beautiful post about fractal scaling in layer 3s, basically bringing this topic of layer 3s to a lot of discussion. Now, if you want to build a layer 3, what you need is a verifier written on Starknet that can verify Stark proofs. So there's another project that is dedicated to that, writing the verifier on top of Starknet. That's done by Herodotus. So Herodotus are doing two very cool things. One is writing this verifier on the Starknet, and another thing, sorry about this, that's very interesting is running. So they're doing two interesting things. One is using the stone prover as part of the Sharp system in order to provide storage proofs, and they've already proved all of the headers of Ethereum, and that's part of their storage proof system that uses stone. And then the other one is that they're writing a stone verifier on Starknet. So that's another cool project. And then another one is allowing client-side proving. So in Goyama, which is a team that also specializes in GPU and general hardware acceleration for ZK, is writing or adding GPU support to accelerate stone proving done on the client side. So you can use your GPUs to prove, on your machines, Stark proofs at a high rate. And there are also conversions into Rust of the code that is currently in C++, and also integrations of Stone with Madara, which is a standalone Starknet app chain that is already in the works. So an adaptation of Stone into Madara is being done by Moonsun Labs. So I really, really hope that those of you looking into cool projects to do, so you'll just see that there's a whole bunch of projects that build on Starknet and on the Stone Prover, and I hope you'll find one of them. Or if you want to find some other project, you're more than welcome to reach out to the Starknet Foundation or to us at StarkWare in order to offer some things and explore if we can do some stuff. So with this, we're going to answer, let's see if there are any remaining questions, and then we will wrap this up. So if time remains, I would be interested in discussion about how changing field size would affect current Cairo programs and change performance profile. So it's a terrific question. I'll try to speculate. One part, how it would change Cairo programs, not at all. The whole point of Cairo would be that, especially, well, depending how you write it, but if you don't make use of specific felts, then it's going to be completely, again, I'm speculating because we don't have it, built out or even spec'd out. But the idea is to have things backwards compatible in a way that as long as your code doesn't rely specifically on the specific fields of a given field, you can just compile it and it will just run just the same. Now, in terms of performance, I would say, I would guesstimate that in terms of raw proving power, going down to smaller fields should give you between, let's say, 1 and 2 orders of magnitude of improvement in latency, roughly, ballpark. So between, when all is said and done, let's say 10x and 100x nominally, somewhere there in between on the proving side. So overall, things should be improved. I will point out that at least in our applications today, the prover throughput and latency are not the blocking points for us. They are other places in the stack. So it's not like this is something that we need, but certainly if you talk about like real-time applications or proving very high throughput client-side games and so on, then every 10x improvement could be extremely meaningful. But Gidi, what do you think about this?
Okay, thank you for muting. I think if you want to take a look at the toolchain today as it works for Cairo, programs are not directly compiled into Chasm. They're actually compiled into Sierra, and you have specific types that you can use. So if you're using a FEL 252, then clearly you want to prove something about a large field. If you're using a U32, then you're actually interested in proving something much smaller, and it doesn't necessarily need to be compiled into an underlying virtual machine that uses a smaller or larger field. So if you are accurate about the field, about the types that you use in your Cairo program, that will eventually allow a small field prover to be more performant for your specific program. In the grand scheme of things, today what happens is that when you submit a new Starknet contract, it gets compiled, or you compile it into Sierra, and from there to Chasm, and that's kind of a one-time operation today. So even if the old program was written with only U32, it would still need to be proven by a Chasm that was in the large field. In the future, what we envision is that these Sierra programs would be recompiled, and hopefully provably recompiled based on the same Sierra, so that the underlying implementation could seamlessly become something that would be provable by a prover or a Cairo VM defined over a smaller field. So that's how we envision this improving over time. Maybe initially only new contracts would benefit from that. But the idea is indeed that you don't need to change your Cairo program in order to benefit from a different field prover.
Okay, so I think we're pretty much done. What I'm going to do is in the chat, just post the link to the open source code in case you want to download it and start playing with it. Thank you, Gidi, head of core engineering at StarkWare, and thank you everyone who joined us. We will meet again in 3 to 4 weeks in 2024 to talk about many exciting things happening with Starks and Starknet, among them tokenomics and indeed the question of smaller field provers, and some updates on research there, visions about Starknet and where is it heading, and a lot of other exciting topics. So thank you very much, and Happy New Year to everyone.
Thank you, Eddie.
Now the question is,